All right, so we're both very happy to be here. Come on in a little bit closer so people can see it. All right. We're both very happy to be here to talk to all of you today. We are going to be talking about a story of Rust adoption at the company that we work at. This has really been an evolutionary process and a revolutionary one. Evolutionary in the fact that it is taking a very, very long time, but that's to be expected. And revolutionary in the fact that this represents, for us, really a new opportunity and one that does not come along very often. We are a company that normally invents programming languages, and if we do, it's usually in the order of one per decade that sees the light of day. And so bringing in a new programming language is something that doesn't happen every few months, but really every 10 years or so. So this is a very exciting time for us. But before we get started talking about that real quick, a little bit about ourselves. My name is Ryan. You can find me on Twitter at Ryan_Levick. Say hello. I've been writing Rust for quite some time now, before I joined Microsoft, before 1.0 came out. I was the MC, the very first RustFest. So it is extremely exciting to see so many people here who are excited about Rust. Back in the day, it used to be I would mention that I liked Rust, and people would go, "What's Rust?" And that's happening a lot less often now, which is really, really cool.
Hola, Barcelona. My name is Sebastian. I'm a security software engineer. So it means that I work with vulnerabilities and patching software, those kind of things. And I've been also writing Rust for 6 years now. I actually checked yesterday for how long I've been writing Rust, and I found that my first contribution to the Rust compiler was in 2013. And it was a tiny patch, 4 lines, but it was the best way of learning Rust for me. So yeah, here we are. And we both work for Microsoft, opposite sides of Microsoft. To be honest, we don't even work in the same country. And Ryan works from Germany as a developer advocate, and I work in the Microsoft Security Response Center. So yeah, not really in the same team, but we teamed up for pushing for Rust adoption in Microsoft. And yeah, so we are part of a virtual team that we like calling the Safe System Programming Language that you might have seen in some of the blog posts that we have been publishing. SSPL for short. Yeah.
So we're going to be talking about adoption of Rust today at Microsoft. But before we begin with that, the first thing to talk about is the problem that we're actually trying to solve. Obviously, we don't want to adopt a programming language just because it's cool, just because we too like to write it. As much as I wish that were possible, you don't get very far with that kind of reasoning. And so we're really trying to address a problem here. And this isn't really a problem that affects us as a company only. It's also a problem that we believe impacts the entire industry, the entire software industry. And because of this situation we've got ourselves into as the software industry, that really impacts the entire world, for better or for worse. And this is, we should say, a billion-dollar problem. Really impacts us in an extremely deep way. And I know money is perhaps not the best way to measure this, but you can think of it not only as a problem that causes us to lose money, but also causes everybody in this room, everybody in the world, really a lot of headache and pain. And at the core of this problem, at the very, very core of this problem, is a technology that we've been using in the software industry that has gotten us very, very far and been really, really great at a lot of things, but is really starting to show, for lack of a better word, its age. And that technology is C and C++. C and C++ are extremely great at writing low-level systems. They use very little resources on the machine. They are, in fact, really the basis on which we create our systems today. But the issue with that, of course, is that they are very, very unsafe. And when they were developed, did not really have safety in mind. And when we say safety, really we mean the ability to write secure and correct code with it.
So I'd like to introduce a little about what the Security Response Center does. The Security Response Center is basically an organization in Microsoft which centralizes the management of vulnerabilities. So it means that we work with external researchers, internal researchers as well, to find vulnerabilities in the Microsoft products. We work with the product teams then to fix them and also try to avoid from developers from repeating this mistake. We also work in different mitigations to prevent the exploitation of these vulnerabilities. And we have all this data about the vulnerabilities. For the sake of the argument today, this is a binary classification of the vulnerabilities that we have. I've seen that Peter mentioned this 70% before, so I don't think it requires much introduction. But yeah, around 70% of the vulnerabilities that we patch in our software are related to memory safety. And as you can see, this has been maintained in time, so the problem is not getting any better.
So naturally, the question comes up then, okay, this seems to be a problem that you have vulnerabilities, but how much does this actually cost you? And how much does this actually cost the industry as a whole?
Well, this is a very conservative estimate, and this is $150,000 per issue. You can see this is a lot of money, and this is only for Microsoft. It's not accounting for the work and time that our customers have to spend rebooting machines, installing the patches, and doing everything else that you have to do every patch Tuesday.
Okay, so $150,000 per issue, but okay, if there's only one issue per year, then perhaps that's not too bad. How many issues are we actually talking about?
And only in 2018 we had 468 issues. You can see that this is a lot of money if you make the math. Sorry, if you make the math and times the amount of money per issue. So yeah, this is a lot, and as we can see, the issue is not getting any better. It's actually getting worse year over year, and only in 2019 we had over 470 issues, and the year is not even over yet. Sorry about the mic.
All right, so the issue is getting worse over time. That's not so good. But is it possible that the cost could be even higher than what we're talking about here?
This cost is only for when the good people find the issues, they report it to us, then we patch them, and then everyone is happy. But what if a malware author finds the bug and writes an exploit for it? This has happened like many times in history, but there are a few occasions that it got out of hands. I don't know if you remember SQL Slammer. Back in 2003, it was a worm that was exploiting a vulnerability in the SQL server, then was infecting the machine and using that machine to infect other machines. Then we had Configure that was exploiting also, as to your surprise, a buffer overflow in one of the RPC servers of Windows, infecting the machine and then also using that machine to distribute the virus to the other machines. And most recently, WannaCry. I don't know if you were affected by it or your organization, but you probably know more than one person that was affected by it. What this worm was doing was exploiting the SMB server of Windows, then was infecting the machine, encrypting all the files in the disk, and asking for, I think it was $300? Yeah, $300 and to decrypt the files. This worm distributed to over 200 countries only in the first week. To give a an example, the national healthcare system and PCs of the UK were affected by this ransom. And there is an estimation that it costed the organization, that organization only $96 million. And the global estimate for this ransom was around $4 billion. Yes, that's what you're seeing, is 9 zeros. And some people put the estimate even over $8 billion. So as you can see, this is a lot of money.
All right, so we have these memory safety vulnerabilities that are causing lots of headache and pain, upwards of $4 billion at a time. That's really not a good thing. But how can we actually fix this issue? And there's been many ideas that have occurred over the years, some better than others, and we're going to talk about a few of them. So the first bright idea that was had, and is an idea that you often see on a particular orange website nowadays, is that we need better programmers. All right, we're done, thank you. No, please stop. This does not work. We need better programmers is not an answer to this. Training does help. You can try to mitigate some issues by making people better at writing secure software. So we're not saying that you should not train people, but this is absolutely by no means a way to address this issue. You can have extremely highly talented, highly trained individuals writing code, and they will still make mistakes. So, no. Now that is out of the way, that's good. What about another great idea? And this one does work a lot better. That is the need for better analysis tools, and is something that has been happening over the years quite often, both static and dynamic analysis tools that allow you to look at a program and determine if it has vulnerabilities before it ever reaches anybody's machine to actually run. And this works fairly well over time, and is something that we still want to actively invest in, because no matter what happens after we leave the room today, the world will still continue to have plenty of insecure code in it. People will continue to write in insecure technologies, and so we need the ability to take a look at that code and determine if it has a vulnerability inside. But these tools are not perfect, and we are convinced that they can never be perfect. So there's really only one idea left that we can actually use, and this is really the only way that we can address this issue fully. And that's the idea that we need to make these issues impossible to introduce in the first place. And over time, there's actually been a lot of active research into this area, how to make these issues impossible. And there's a few things that have been introduced in software that allow them to not actually occur.
Okay, so I think to understand the issue, we have to understand the problem. We have to understand the problem to find a solution. So we can classify the memory safety vulnerabilities in two big classes of vulnerabilities. And one is related to spatial memory safety. What does it mean? That when you have a pointer or a buffer that's some type of memory, and it usually has a size, it's not infinite. So when you try to index out of that buffer or pointer, you get what C developers call undefined behavior. So it means that everything is wrong, and it's not doing what you are expecting it to do. For fixing this issue, there is a clear way that most languages have now. That's a runtime check. When you allocate memory, you can embed that information in the pointer or in the buffer. So now you have a rich pointer or fat pointer. So when you try to index that pointer, now you have a runtime check that you don't have to do anything. If the index is outside the bounds, it will fail the memory access, and nothing bad will happen. And The second type of the memory safety that we can talk about is spatial memory safety. This means that when you claim memory or when you allocate memory, that memory will be valid only for some time. And once it gets freed, you shouldn't be using that memory. But sometimes in the languages, you don't clear the references, and then you can still access it. And there is an easy way of solving that a lot of languages use, and that's using garbage collection. What does it mean? That you can claim memory, but you cannot free memory manually. You expect the runtime to free the memory. And this is basically always leaving the memory there, and then you will have this program inside the runtime that will go and find the memory that is not used anymore and free it.
But of course, garbage collection does come with its downsides. There are a whole class of programs out there where a runtime, like a garbage collected runtime, is not really acceptable. So if you're writing an operating system or perhaps a really low-level system, like a database or something like that, more often than not, you don't want to pay the penalty of having a garbage collector, which comes with performance penalties and also comes with penalties for not really knowing when certain things will run. And that's just oftentimes unacceptable. But we believe that there is a technology out there that allows us to kind of have our cake and eat it too. And spoiler alert, it's Rust. Rust is not particularly exactly perfect in this regard, and we're going to talk a little bit about the caveats to this, but Rust does allow us to write performant systems programs in a safe way. And to look into what Rust actually gets us in practice, we'll take a look at this.
So, I mean, Ryan was talking before about making these issues impossible, and that's kind of a hard thing. But what if we could isolate what's unsafe from not unsafe, what's unsafe from safe? And when we are looking at the C++ code base, we find that 100% of the code base is written in unsafe C++. You don't have no way of isolating what's safe from unsafe. And for example, when we are talking about software, we have to make threat models about that software. What does it mean? That you have to make an analysis of how the software can be attacked. If we are talking about a browser, for example, for a browser, the threat model is that every website can be malicious. If we are talking about a kernel, we have to start from the ground that each program running in user space will be also malicious. So that has to protect. It has to protect from every program. And after you have this threat model for these two examples, you come to the conclusion that almost all the code is exposed to the malicious input. And when we look at Rust, there is a clear boundary of what's safe and unsafe. And this is a big advantage for security software engineers like myself, that we have to audit these code bases. And we made an analysis of the most used crate and came to the conclusion that the amount of lines that were unsafe in the top 200 crate was only 1%. And I remember I was at RustConf watching Jeremy's talk, and he was talking about the Rust adoption in Facebook, and he was saying that there is a threshold that the technology has to overcome to be 10 times better than the next technology available. And as we can see here, Rust is not over that threshold, but we can consider that in this aspect it's 100 times better than the next technology available.
But of course, we're at RustFest, so we're kind of preaching to the choir here. Mostly everybody in this room probably already understands this. You may not have selected to use Rust for this property, but you've probably heard about it before. And so let's just say, for the sake of argument, that we're going to use Rust. We have chosen it. We've been able to convince ourselves that this is a good thing to adopt. What does that actual adoption process look like? And this is really where it actually begins. Because while Rust might present a very interesting opportunity for us as an industry, we have a whole ton of C and C++ code written out there, and we can't just snap our fingers and have it written in Rust. It's going to be a very, 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 very long time until that goes away, even if we were all 100% convinced that that's the right thing to do. So when we talk about Rust adoption, the first thing that we should take a step back at and look at is actually how do languages get adopted? And particularly, how do they get adopted in existing large companies? Because if it's a startup, it's quite easy. You can just choose to use a new technology because you haven't written any code before. But if you have a huge code base that already has C and C++ in it, what is the process actually like? And the issue with this is the following. You have costs and you have benefits. And I don't know if you can see it, but down there it says benefits, but they're very hard to see. The costs are quite clear. You have the costs of actually introducing the code inside of your code base, of introducing the compiler inside of your build system. These are all very clear costs and are actually very easy to reason about how much it will end up costing your organization to actually adopt it. But the benefits of introducing a new language may not be so clear. If you're introducing a new language because it has a great type system, and you think that that type system will not introduce as many bugs as the current language you're using, well, how do you actually prove that? It's extremely difficult to actually measure the impact of something like a more advanced type system. But at the end of the day, this is what makes Rust more adoptable. Because for Rust, that picture looks more like this, where the costs are still quite clear, but at least this one benefit that we've been talking about of memory safety is extremely clear. We know that Rust will get us much further along to writing memory-safe code, and we know that memory-unsafe code leads to billions and billions and billions of dollars of damage. So it's quite easy to go to people and say, how about we stop spending billions of dollars on this stuff? And they go, sounds good. And of course, we've only written benefit here. That's not to say that Rust doesn't have other benefits. It's just to say that those are harder to talk about and harder to convince others in a large organization to bet on Rust because of them. So really, when it comes to adopting it in a large organization, it really is enough to just talk about its memory safety properties in order to convince others that it's worth adopting.
Yes, so maybe, just maybe, and we shouldn't be writing security-critical software in C++, because of the things we were mentioning before. So now the debate is, what do we use for writing the security-critical software, and this is probably Rust. I mean, Rust has, you can write performant code, and having all these extra things that are related to the memory safety of the language. But we cannot just ditch everything that we did till now and start over with Rust. So what we can do now, do we just continue using the technologies that we were using before, especially C++, or we can maybe try integrating Rust with our existing code bases and technologies. This means that we have to integrate Rust with our infrastructure. And that's not easy because Rust is not just a language. Rust is a set of tools that you are bringing to your infrastructure. And especially for Windows people, and Rust comes with this beast, that the compiler backend that Rust uses, that is LLVM. And LLVM has started with great support for Mac, BSD, then Linux, but Windows support is not really there. And one example is, for example, LLVM didn't have a linker for Windows binaries till only a few months ago. Continuing on this line of bringing all these Rust tools to your infrastructure, is that we have a lot of tools that we have to run in our pipelines to generate the binaries and to check that the binaries are okay. An example is that we check all the binaries that we ship to our customers for performance. That means analyzing all the binaries at runtime, checking that they are doing well, and sometimes rewriting those binaries. It means rearranging the basic blocks that are inside so they are more performant and more cache-friendly. And the problem that we have with those tools is that those tools are used to analyze binaries produced by MSVC. And obviously, you cannot just expect that LLVM and MSVC are generating the same type of binaries. They have different name mangling. They have different types of symbols, and they arrange the information in a different way. They have different heuristics for generating the code. So this is a whole new set of tools that we have to adopt. And continuing on this line of tooling, we have also built systems that have been optimized for many, many years to perform well and to comply with a set of rules that we have in our build system. Just for a second, imagine, and theoretically, that you want to include a Rust component inside Windows. And these challenges are that when you want to use Rust code there, and you have obviously cargo, which people use to build Rust binaries, and cargo is a great tool. I mean, who can imagine using Rust without using cargo? You are losing half of the features. Cargo is a great build tool and a great package management tool, but it has to be integrated in an existing build system. We cannot just let cargo manage our whole build system. And obviously, for cargo, there is Rust code, and not Rust code. There is nothing else for cargo. And continuing on this line, we must be able to interoperate with the existing software, as I was mentioning before. And the software is usually written in C and C++. And sometimes you have a clear boundary between these different DLLs, maybe. One is written in C and the other will be written in Rust in the future. And Rust, fortunately, is very good at interoperating with other technologies because it supports most of the APIs supported by C. And also another great tool that comes with Rust is Bindgen. Bindgen lets you take a C header and generate a Rust binding for it. But the downside is you have now all these unsafe binding that you have to make a safe wrapper around it. So maybe the idea is that in the future we can kind of guess if we can make a safe wrapper around these C headers. And the last one is it's crazy, but there have been many technologies to make interoperability language agnostic. These are libraries like COM and WinRT. These are well-defined API standards. And because, C++ didn't have a well-defined API back then. And these are things that the community have been working on. We analyzed most of the things available for COM, and we decided to to also write another compiler that we released this month, I think. Yeah, so we are getting there with interoperability. Then we have also weird problems that common people don't have. And well, actually, common people is a bad description, but individual developers maybe don't have, or small companies, but big companies put processes in place to prevent errors from happening. And it means that everything that you bring into the company must comply with a set of rules. And one of them is having a trusted toolchain. When you are developing with Rust, you download Rust app, you execute it in the PC, and then after 2 minutes, well, depending on your internet connection, you have Rust available to be used. But when you are bringing Rust into another build system, and like the Windows one, you just cannot pull a binary from the internet and run it there. And even more if this binary is connecting to the internet, pulling even more binaries from there. So using Rust up there or putting the Rust compiler directly into the build system is not an option. It means that we have to build our own tools. And this is a big challenge because we have to start from a trusted source code and a trusted binary, and then build the trusted binary that we can use in our build system. The following one is about, these are all examples, and there are many more, but we have binary security policies. All the binaries that we ship to our customers comply with a set of rules to make them more secure. So, for example, all the binaries that are shipped have DEP, ASLR, and a few other memory exploitation mitigations enabled in them. An example of it is control flow guard. And control flow guard is something to protect the control flow of the program, so malicious input cannot hijack it and then do something that the program was not programmed to do. And this was a mitigation that wasn't available in LLVM. Now we can happily say that we made this mitigation and contributed it back to LLVM, and it's been in master for, I think, since last week. And we hope we can enable it in Rust in the following months as well. So super happy about that. And then we have also the humans challenge, if we can call it like that. And this is probably the most interesting to me, that I'm used to deal with machines, but not really with people. And this is the first problem that you have is convincing people of using a new technology. And fortunately for us, Rust is a very adoptable technology. But when you try to tell someone, hey, maybe we should use Rust, and because it's memory safe, the first thing that they think is, hey, we already have C# for that. Why are you suggesting this? And then you have to start explaining that Rust doesn't have a garbage collector, and it doesn't have a runtime, and it's more similar to C++ than actually C#.
And the last point is you have to be able to train people who might be used to writing C and C++ for 5, 10, 30, 40 years, and be able to show them how to write Rust code that they might not be used to writing. And the good news about this is that when we've introduced Rust to seasoned C++ programmers, they generally are able to get it rather quickly because it kind of just formalizes things that they already have in their head. When people are coming from other backgrounds, it might be a little bit more difficult. But while the learning curve is quite steep, generally people get through it, and once they're through that learning curve, they're quite productive, which is really nice to see. But we've been talking for a while now about the challenges that we're facing as a company, and okay, that's great, we're going to face these challenges, but there are also challenges that we, as an entire Rust community, also have to face when Rust becomes more and more adopted. And one of the first things to talk about is the idea of governance. really we want to, as a community, ensure that Rust is owned by the community and not by any one particular entity. And as more and more companies come in and want to use Rust, there's always the temptation to start taking control. And that's something that we do not want. We want to ensure that Rust stays in as a community-owned project and directed by the community, because frankly, it's gotten here because of the community, and the community is the best one that will be able to take it forward from here on out. And really what this means is that we want to take the community principles that we as a Rust community have established over time and really establish them in more or less a formal way. And of course, there's great work going on already from the governance working group and a lot of talk happening in many directions around this. And we're really excited to see this go even further. And with that, over time, Rust will continue to change. We just had async await come out yesterday, which is really exciting. The language that, as it looks today, although it still compiles, looks different than it did in 1.0. And the language will continue to change over time. But we want these changes to continue to benefit the majority of people. We've already shown that we have some rather interesting and perhaps esoteric needs that maybe most people in this room won't ever need in their language. And I'm sure that we'll be introducing or helping to introduce some changes to the language that make the job of creating Rust software at Microsoft easier. But we want these changes to, at the very least, not disturb anybody else who doesn't need them, and at best, make sure that they are actually helpful for everybody else. And so this is extremely important. And going back to the idea of community, we want this design to be, again, community-driven. So just like the RFC process has happened in the past with input from everybody in the community, if they're able and willing to give it, we don't want some backroom community design happening and then, plop, there's changes to the language all of a sudden. We want these changes to be driven by the community as a whole. And the last point that we want to talk about is this idea of reluctant Rustaceans. Presumably everybody in this room is here voluntarily. At least I hope so. But in the future, that might not be the case. I started writing Rust because I wanted to, not because I had to. But in the future, there probably will be people who have to write Rust, and they may not want to. What does that do to our community as we introduce more people into it who are kind of reluctantly there? And the real challenge with this is maintaining what I like to call the community spirit, or the thing that we already collectively have as a community, the thing that, in my opinion, makes Rust awesome. How do we continue to have that as more and more people who are not necessarily there by choice interact with us and come into our community? Okay, so we're at the end now, and this is really where we ask you to come talk with us, come engage with us. Even if you work for a small startup or you're just a hobbyist programmer, maybe you're not a software programmer at all, you just like to use Rust in your free time, all the way to up to you're working at a huge company and have some of the similar problems that we have. We'd love to talk with you, hear from you, work with you, and really what we want to be as Microsoft is a part of this community. We're not here to take over, we're here to be a part of it and work with all of you. So, thank you very much.